Hey everyone! In this lesson, we are getting started on probably one of the most important concepts that we're hitting in integral calculus. So, if you go to lesson 27 and read along, it says here, in differential calculus, which is everything that we did with derivatives, we were concerned with finding the slope of the tangent line, also known as the derivative, at any point on the curve. That was our big deal in differential calculus. But in integral calculus, the basic problem is to find the area under the curve. That's the big story in integral calculus. The area under the curve, sorry, didn't mean to cross that out. The area under the curve is the area between the curve and the x-axis between any two values of x. So for example, if we take a look at this curve over here, if I wanted to look between x equals 0 and x equals 4, in integral calculus, we're concerned with the calculation of this area. We want to know what is this area under the curve. And what this has to do with integration, we will discuss during this lesson and beyond. But this is kind of setting up the story. This is a really big deal. This is a really big concept. All right, so let's take a look at what we have here. Here we're given a curve, f of x. Okay, and we're going to call f of x, this is actually the graph of x squared plus 1. And if we want to estimate what we believe the area is, what is the area between 0 and 4, area under the curve between 0 and 4 of f of x, you may start thinking in terms of rectangles. Okay, because this isn't a shape that we can necessarily calculate the area of. So you may start thinking, well, this is like about this much of the rectangle, give or take this white space, and if I can make another rectangle here, I can calculate that area, give or take that white space, and you can make a pretty educated guess of what that area is. So in these graphs, I have the curve with two rectangles drawn. What you notice here is that you have what's called a lot of error. This area, or this section where I've put a star, is error, meaning this is really what we want and this is what we don't want. So if we look at the graph with 4 rectangles drawn, we notice that even though we have increased the number of rectangles, we have less error. And this one over here has 8 rectangles drawn. So again, even though we have increased the number of rectangles, we have decreased the error. In turn, our area under the curve is more accurate. So what would I be doing with these rectangles? Well, what I would be doing is I would be calculating the area of each rectangle and adding them up to create an estimate for the total area under the curve. So if we take a look at the 2 rectangles, the area of a rectangle is length times width. So this rectangle is of length 2, or I guess you can call it width because it's wide. Width 2, and length is, in this case, 5. How do we know that it's 5? Well, A, it's on 5. And B, remember that it's y equals x squared plus 1. And when x is 2, y is 5. By plugging that in, 2 squared plus 1. So when x is 2, y is 5. So this rectangle has an area of 10. Now we have another x value of 2, and then our y value is, this is 4 right here, our y value is, what is it, 4 squared plus 1, which is 17. This is 17. So 2 times 17 is 34. Now why is this 2 and not 4? Because we're only going from here to here to build this rectangle, and that is 2 units wide. When we do go 2 units wide, x is 4, going up to 17. Why 17? Because 4 squared plus 1 is y. And then our estimate is this area plus this area, so our area estimate is, in this case, 44 units. Well, this is not a good estimate, guys, because we have a lot of error going on here. So we'll do the same for each of these. This is tedious, obviously, because you have to do that 8 times. But you'll notice that your widths are all the same. It's just that you'll have to calculate each length, you know, depending on, it's y equals x squared, so you're going to plug the length into the width. And you'll find all those areas and you add them all up. And obviously, of all of these three, this one will be the better estimate. So would you have to go through this process by hand? Kind of. Let's go ahead and take a look at the bottom of the notes here. It says, as you go through the process, several things should be apparent. First, drawing the function and the rectangles, they're not really necessary. Okay? Drawing the functions and the rectangles are not really necessary because we have a function, in this case y equals x squared plus 1. If we know the input, we can come up with the output. If we know the width, we can come up with the length. Next thing that's important is that the more rectangles you create, the more work you have to do. And we saw that when we were thinking about maybe doing this for the 8 rectangles. It's going to be a lot of work. But also, the more rectangles we create, the smaller the error in calculating the area for each rectangle. So even though it is a lot of work, it is a better option. It gets us a better estimate of the area because we have smaller error as we get more rectangles. And with that being said, comes this really important bullet point. As the number of rectangles approaches infinity, the error of each rectangle approaches 0. So as the number of rectangles gets infinitely large, as you put an infinite amount of rectangles in here, the error of each rectangle approaches no error because the rectangles are getting closer and closer to being right under the curve. And if you have infinite number of errors, each approaching 0, the total error should approach 0. If each of these errors is approaching 0, then adding them all up should also approach 0 because 0 plus 0 plus 0 is 0. So what we're getting at is that the more rectangles you produce under the curve, the closer your area is to being accurate. The less error you have, the more accurate you are. Okay, so let's take a look at this. If you have no error, you have the true area. So area is equal to the limit as n approaches infinity, where n is the number of rectangles. As the number of rectangles approaches infinity, the area is the sum of all the areas of those rectangles. So n is the number of rectangles. N is the number of rectangles. We're starting with one rectangle going all the way to infinite rectangles. Okay? And capital A sub I means area of whatever rectangle you are. So if you're on the first rectangle, it's area of rectangle 1, area of rectangle 2, area of rectangle 3, all the way to the area of rectangle number infinity, which isn't really a thing. But basically, what we're saying here in this notation is everything we said up top. This means sum or add up. So as n approaches infinity, the limit as n approaches infinity, as the number of rectangles approaches infinity, the area is the sum, the true area under the curve is the sum of the areas of all the rectangles. Well, the area of all the rectangles is base times height, and base, which was the width, and if you remember from up there, our width was 2, 2, 2, 2, and what changed was our height, and our height changed on where we were. So if we kind of scroll back up there for just 1 second, our height when we were at x of 2 was 5, but when we were at x of 4 it was 17, but our width was the same the entire time, 2, 2. Okay, and our height changed depending on what rectangle we were on, which was dependent upon what x value we were on. So base is a constant multiplier that we can pull out. So this is the definition of the true area under the curve. okay? And we're going to explore this quite a bit this week and a little bit of next week. But area under the curve is the limit as n approaches infinity, where n is the number of rectangles, of the adding up of the base times heights of every single one of those rectangles, starting with the first rectangle, ending with the infinite or last rectangle. So I want to show you a quick video, and let me go ahead and pull that up for you. So what's happening here, and what I'm trying to show you here, is you've got this curve, and what's changing here is the number of rectangles. It's going from 1 rectangle to 100 rectangles. And I don't think I can zoom in here, but basically, as the rectangles get lower, you see the error. And try to slow it down there. You see the error kind of sticking out. And as the rectangles get higher, you see that the rectangles, even at 100, the rectangles start to almost fit nicely under the curve. So we're going to explore that a lot more, like I said earlier, and I hope that that laid a little bit of a foundation as we talk about Riemann sums tomorrow in class. Thank you.